Okay, we are recording now. Welcome back. Today, we're finally going to finish up with this optimization kind of part of the course. We're going to finish up with mainly this gradient descent business. And maybe we'll get a little bit into the next part, which is kind of resolving an issue we're going to see at the end of today's class, which is how do we pick the function class? Roughly speaking, we're going to see that, so far we've been dealing with these linear functions. And you can imagine that not all data follows a linear function. Sometimes it might be more complicated. And you're going to want to pick a function class that's more complicated. But we're going to see that eventually, if you take this kind of to the extreme and you make the function class extremely complicated and you allow very, very weird looking functions, you're going to be able to fit the data perfectly. And like intuitively, you'll see that this probably means you're not doing great on new data because, visually we'll see that this function looks probably not like something you'd want to actually use to predict new data. It's going to be this weird oscillating looking thing. And so roughly speaking, we're going to see there's going to be kind of this trade-off between picking a very complicated function class, or in other words, fitting your data almost perfectly, and doing well on new data, new examples. And that's going to be kind of the next topic we get into. But let's, before we get there, let's just finish up this whole optimization thing. And what I want you to keep in mind is that this empirical risk minimization algorithm is really what we're trying to develop. We're trying to develop, like, how do we kind of implement its parts in different ways depending on different situations and cases that we're in. And we saw, like, basically for this course, and this is kind of standard for most machine learning, like supervised learning settings, you're going to use the sample mean to estimate your risk. So that's going to be your empirical risk. But afterwards, there's like various choices for this optimization procedure. And the obvious first choice you want to make is by just solving the system of equations. And what I mean by this is taking derivatives, setting them to 0, solving the system of equations, and just finding the true minimizers. However, what we saw is that for more complicated problems, and by more complicated, this means when we pick more complicated function classes or different loss functions, these closed form solutions aren't going to exist, so we're going to need something else. And so really all we're trying to do is develop ways to optimize, and by optimize, we're really focused on minimizing this empirical risk, which you should keep in mind is just a single number that hopefully you've been convinced tells you or accurately describes the quality of your predictor at predicting new data. And this empirical risk is an estimate of that number. And so we're trying to minimize this quantity. Okay. And we went over all this gradient descent business on how to do that. So let's review that gradient descent algorithm. This was the pseudocode. And we called this batch gradient descent because it used an entire data set to take one step of the gradient, and then it kept on iterating over and over again. Okay, so how did this look? So as our learner should, it takes as input a data set. And keep in mind, this algorithm here, this is how you're implementing your learner A, the calligraphic A. That is your function, and it's being implemented via this algorithm. This is the way we've implemented ERM, empirical risk minimization. Okay. So as it should, it takes in a data set. However, we notice that there are other what are called hyperparameters that can change how your algorithm behaves. And one of those is the step size. And the other is the number of epochs or iterations that you're going to run gradient descent for. And the algorithm is quite simple, actually. You start with some initial kind of guess at your minimizer. This is like the predictor that's going to minimize the empirical risk. And then you iterate by applying these gradient descent steps. And this is what is often referred to as like your learning. And this is why the step size is often called the learning rate. So this is kind of like you're doing T steps of learning. And visually, that you should associate that with, you start with some poor initial guess to the kind of optimal line that fits the data. And then you're iterating to try to find a better fit to the data. And that will look something like this procedure. And if you chose a good step size, then each one of these iterations will produce a vector, which describes your predictor, that is kind of closer and closer to fitting the data, which, once again, for us, that means that its empirical risk is small. Okay, so this quantity right here, not the gradient, but the empirical risk, should be a number that, once again, you should hopefully be convinced that it measures how good does a line fit the data. And so like this green line is going to be kind of the one that minimizes the empirical risk, which means that if you take all the data points, you take their squared distances towards the line, that is minimized. This is an important mapping you have to make between like visually what it looks like for your predictor to fit data and how this single number is relating it to that. So a smaller number means better fit to your data. Okay, and there's another plot we drew, useful to think about, which is that if you chose a good step size, that if you increase your number of epochs, then your empirical risk, your estimate of the expected loss, it should be increasing, should be decreasing. And then it will eventually kind of converge to this minimum value. It is exactly the minimum empirical risk you could imagine to get based on the function class you chose. So like intuitively, a line cannot perfectly fit through all the data points, right? But we're going to see if we pick some more complicated function, maybe like this, then maybe you can fit all the data points. And we'll be able to get this kind of dotted line to be closer and closer to 0 with various trade-offs, which we'll talk about right at the end of the section. Okay. And then we talked about how why do this gradient descent stuff if you had a closed form solution? And it turns out even then there's some advantages, which is in terms of the computation. And the way we thought of this was on a computer, the way this is like thought about is you think about a computer as having these kind of elementary operations that take constant time, such as addition, subtraction, multiplication. And we want to count the number of those operations. And so we did that last class, and I'm not going to go over that. But for the closed form solution, we did that calculation. We found out that for an input of size n, and by input I mean a data set with n data points, and for a feature, which implies that your weight vector, your parameter vector describing your predictor has d dimensions, well, the scaling is as follows. So as the data set size increases, or the dimension of your parameters increase, the number of computational kind of steps your computer is going to need to make scales as n d squared plus something like d cubed. And this is what this big O says, it scales of this order. So you can, maybe it scales like 3 times this amount, or there's some extra constants added, but it's around this rate. And that should obviously make sense. You know, if you increase more data, you're going to have to loop over it more data. And if you increase, you're going to have to do like matrix and vector multiplies that are of bigger dimensions. And then we did this also for this batch gradient descent algorithm. We did that analysis, and we found that there the total number of computation steps is size of the data set, size of your parameters, the dimension, and then the number of epochs, which of course also makes sense. The more iterations you do of gradient descent, it's going to go up, and it goes up linearly because you have just one for loop over it. And if you compare these two quantities, which is the batch gradient descent algorithm and this closed form solution, you will find that one case analysis, which is all we're going to do for this class, is if your number of epochs is smaller than the dimension of your parameters, your weights, then the runtime of batch gradient descent will be less, like the number of computational steps. And yeah, in some problems, this can very much be the case, that you'll only need like 100 steps of maybe gradient descent, 100 epochs, but your dimension of your features or parameters can be in the millions or something. Okay. Yeah, so that's where we got to. And the next thing we're going to talk about is how to further kind of improve this computational efficiency by an algorithm called the mini batch gradient descent. And then after that, we'll talk about using a bigger function class that's not just lines. Okay, so let's go back to gradient descent and see where we can kind of improve this algorithm. And the improvement comes when you start to think about what happens when you have a really big data set. So when you have a really big data set, the way you use the data set is to calculate the empirical risk and then take its gradient. And if the data set is really, really big, or like, let me say this in another way. You know, as you scale the size of the data set, your empirical risk estimate gets better and better. But there's going to be some point where, let's say you have like 1 million or maybe 10 million data points where increasing it to 1 billion might really not give you a huge benefit in terms of the quality of the estimate. However, the number of computational steps to do that calculation can be very high, and in particular, calculating this gradient. And so you can imagine there's going to be some kind of like balance, some like optimal point of how many data points you're going to want to use for this gradient kind of estimate, and the number of computational steps you make. And so the rough idea is we're going to break up our data set into smaller chunks and then do this calculation with a smaller chunk of the data set, and therefore we can do more gradient steps, each of which is kind of with a worse estimate of this empirical risk. Okay, so that's called mini batch gradient descent. So let's work through that. And yeah, the question was like, are we doing worst case analysis for the computation? And the answer is yes. This is like the worst case runtime, I guess. But yeah, that's all I'll say. And what that means is that the runtime will be no larger than this. But in some cases where maybe your vectors are sparse or your matrices are sparse or things like this, those matrix and vector multiplies can be done more efficiently. But in the worst case, this is how long you'll take. Okay, so next algorithm, mini batch. And this is why we called the last one batch, because it used the whole data set, mini batch, gradient descent. And this is really what's used in practice. Because you can imagine you probably don't, if you have a data set of like trillions of examples, like the whole internet, you're probably not going to want to just, go through the whole thing, calculate a single gradient, which will take literally, matters how many GPUs you use, but it could take, days or weeks, and then you do one gradient step. That would be quite disappointing. Okay, so how this is going to work now is we're going to have this data set, and I'm going to write it in just like a visually different way to make the point clear. So I'm going to arrange it into kind of rows that are the mini batches. So I'm going to take our data set, and we have this point x1, y1, right? And then we go up to, and instead of going up to the nth point, I'm going to decide on a mini batch size. I'm going to call that batch size B. And we're going to go up to the bth point. So this is the batch size. Should make complete sense. If you had a batch size, let's say you chose 100, then you would take the first 100 points in your data set and kind of group that into a batch. And then you're going to go from B plus 1 until two times B. And you continue this process until you get to the total number of batches that you can have until you reach n. Okay. And yeah, let me write it like this, and we'll erase some things in a second to make it clear what's going to happen here. So we get to like m minus 1. M is going to be, yeah, let me write these names. So down here we'll have B, right? That was a number. Maybe I write it like this. It's an element of the natural numbers that you choose. And this quantity is called the mini batch size. And then, of course, there's going to be some amount of mini batches, and that's going to depend on B and the number of data points you have n, which is this m that I'm using above. And so m is going to equal to n over B. But, okay, let's just, yeah, n over B. But you can imagine, let's say n is like, I don't know, 101. And B is 10. Well, then 101 divided by 10 is not an integer. So it'd be very weird if you had 10.1 mini batches. So what you're going to do is you're going to take the floor, which just means round to the nearest integer. And that's going to be the number of mini batches we use. So this is the number of mini batches. Okay, so now we can continue filling in our picture. So we have this guy. Yes, of course. You have to multiply the batch size by m minus 1 plus 1, right? Just like here. Oh, yeah. This is all good. So this would have been like 1 times b plus 1. This is now the m minus 1th one plus 1. And then you have y, m minus 1b plus 1. And that goes all the way up to m, the mth mini batch, b, and y, mb. Okay. Okay. So far, what we've gotten to, let's look at this quantity here. M times b, right? We can look over here. M is always you rounded it down. So if you do m times b, you're always going to get a number less than n. So this is always going to be less than or equal to n. So if n divided by b is an integer, you're going to get m times b equals n. Otherwise, you're going to get something smaller. Okay. And then what's left is some extra data, which will, in general, be smaller than of size b, but can sometimes be exactly b and so on. So this extra bit of data that would be here, we're just going to throw it away. Okay, so that's going to be our way of using this. And that's like in practice, you don't throw it away. But for this course, and just for writing this, we're going to throw it away because everywhere you're going to otherwise have a case, which is if it's not divisible, if n is not divisible, if it's not an integer, then you have to do this other different equation, and it's just very annoying. But the principle is really the same. And you can imagine if you have many of these batches, you're not losing much by throwing it away. So that's how we're going to implement things in this class and do this. But you can imagine seeing questions on like your assignment or midterm or something about what's going to happen if you keep the last mini batch and how does things look. Okay, but this will make everything a lot cleaner. Okay, and apparently I have an example here, so let's just write it, why not? So let's just do a specific case like n equals 8, b equals 2, and then your calculation for m, the number of mini batches is 8 divided by 2 is equal to 4. And visually your data set here, like it actually is an integer and everything works out very cleanly. And so you get x1, y1, x2, y2, x3, y3. Okay, for the sake of time, I'm going to change this to 6. But this hopefully makes it very clear what this looks like. And yeah, you should think of this guy as like mini batch 1. This is called your mini batch 2. And this is your mini batch 3. And so we're going to have an internal loop in our algorithm, as you can already imagine, that's going to do this iterating over mini batches. So yeah, this is like mini batch 1, mini batch 2, mini batch 3. Okay. And so now we're going to use this mini batch to get kind of an estimate of the risk, an empirical risk estimate, but only using the data points in that mini batch. So we're going to have like this L hat of W guide like before, but now we're going to index it with little m, indicating the mini batch we're using. Okay. And the way this works is now how many points do you have? Well, each mini batch consists of b points. So you have you're going to divide by 1 over b for your sample mean. And now you're going to sum. And this sum can look a little bit ugly because you have to choose the kind of correct mini batch you're using here. Okay. And the way this works is if you want to use mini batch m, we go upstairs and we have a look over here. So this would be mini batch 2, right? This would be mini batch 1. So looking here, like, what's going on? Well, if this is mini batch 2, you can see that this has a number 1 out here. And in general, this is mini batch M, and it has an M minus 1. So it's going to be little m minus 1 times b plus 1. That's where we're starting at. And we're going to go till m times b. Hopefully that makes sense. So it's going to be little m minus 1 times b plus 1 until m times b. And you can make sure this checks out. So if you want to do mini batch 1, then you plug in 1 minus 1, you get 0 times a number, so that's 0, plus 1, so you get the first data point, until 1 times b, so you get until the end of the first mini batch. Yeah. Yeah, the difference is that uppercase M is the total number of mini batches, and little-case m, I'm going to write, is an element of the set 1 up to capital M. And you should see this happened with the number of epochs as well, right? Which is the lowercase letter is kind of the variable that's used to index the set from 1 up to the capital letter. Because we want to say for some arbitrary mini batch, this is the calculation. Okay, and then the thing in here, you already know what's going in here, right? This is going to be your loss function evaluating how good your predictor did on those data points relative to the labels. And since we're working with like these linear functions, I'm just going to plug in the exact calculation here, which is you take point xi, you take its dot product with w, and then you subtract yi, and we're going to use the squared loss, let's say. Okay. So yeah, this is like our new kind of empirical risk with less data points. And yeah, okay. And let's see, if b is less than n, then what you should think about is then this kind of L hat of m is a worse estimate, than the original L hat we had, which used the whole data set. And that's for like any m. So we got this trade-off where now we're using less data, so the estimate of the true risk is now worse. Okay, so let's just write out the algorithm now. And the way this is going to work is I'm going to just take the original gradient descent algorithm and add in an extra for loop. And thank goodness I'm doing this on my iPad and not on the whiteboard, because this really saves a lot of time. And you can see that it's exactly the same, and hopefully you're going to see where the slight changes happen. Okay, so everything's the same. So far, what's different? Well, we need to choose a mini batch size, right? So that's going to be another hyperparameter. So this was number of epochs. I'm going to erase that now, because you know what that object is. And now you need to also input mini batch size, another hyperparameter that is swept through when you do this training to find kind of the best mini batch size. Okay, and now you initialize randomly. You do this loop over your epochs. However, within each loop, we now have to do another internal loop going over these mini batches, right? So that's going to look like this. We're going to have to make some room for another for loop. And then we're going to have to index this a little bit deeper. And we're going to have a for, and here's the little m that was asked about. Little m going from 1 until capital M. And now the calculation is not of L hat, but the gradient of L hat of little m. And then this calculation, of course, is not over the whole data set, because now we have a new equation for this. So we're just going to go and like, what's going to change? Okay, so technically you're going to have to do the calculation of the gradient again for this case. But the only thing that changes is the number of data points, and so everything's going to be the same except for your indexing here. It's not going to be I equal 1 to n. So just to really make it clear what the change was, is we're going to take the sum and we're going to change the indexing to not be that, but to be what we have hopefully agreed upon over here. I want to make it smaller. Let's try that again. Okay, let's just make some more room for it. There. Hopefully that's visible. So that's what's changed. Yeah, technically, so like when you're writing in code, right, you're not gonna like make a new variable for each thing. So usually similar with W's, how we didn't index it with T, we're also not gonna index this with M in your code, right? You're just gonna override this every single time. So similar how there's no T here, it's the same story as with this. But of course, this M is still the index in the for loop. Okay, and then otherwise, everything looks the exact same. Okay. And now I'm going to mention one other thing that we're not going to get into detail into, but hopefully it makes some intuition. So you do this loop. Oh, you do this loop over epochs, and then every single time, the way I've said, is you use kind of the exact same group for your mini batch, right? So it's going to be like always. Let's say in this case, you always use the same 2 points to calculate your first empirical risk, and then this one, this one. It turns out, for like estimation reasons, it's actually a lot better if each new epoch, you shuffle the data set around such that like this maybe becomes this data point, this one goes over here, this one maybe goes over here, and so on, such that you have like different mixes, different groups for each mini batch. It kind of makes the estimates like somewhat unbiased. Okay. And that turns out to be a good idea, and I'm just gonna mention it, and this is what you're going to have to do in your homeworks and stuff, and this usually improves kind of performance and stuff. So what's going to happen is before each epoch, you're going to randomly shuffle your data set around and then group it into the same type of mini batches as we saw above. So you're going to have kind of different, you're still going to have, each group is going to be of size B, but it's going to have like different data points each time. Okay. So that's mini batch gradient descent. And just some other notes, yeah? Yeah, of course. If you randomly shuffle and get the exact same data set, you might get the same mini batch again, but it's quite unlikely. And then just some like things to point out. So notice that if your mini batch size is the entire data set, right? Then that implies your number of mini batches is 1. And this implies you're just doing batch gradient descent. So this is, in a way, a generalization of what we were doing before, right? If you pick your mini batch to be the whole thing, you're doing batch gradient descent. Nice. And let me just mention the other case, which is the other extreme is if b equals 1, so you're using a single data point each time. Well, then the number of mini batches is n. And this is often called SGD, or stochastic gradient descent. Okay, so this is stochastic. And so you're literally only using one data point to estimate the risk, and then you take a gradient step size. And yeah, and usually in practice, something in the middle is a good idea. So something, I don't know, they'll use like 32 or 64 for the batch size. And you'll play around with that change in the assignment too. Yeah. Oh, excellent. Yeah. I'm not surprised that I missed that. Thank you. So of course you divide by B. It's smaller. Yeah, you want to do a sample mean with B data points. And on that note, the other thing I should change is probably the name of the algorithm, because it's no longer batch gradient descent. This is now mini batch gradient descent, so I put an M. And we're still using the constant step size. And hopefully I didn't miss any other details. Oh yeah, there's another detail, of course, which is what is M? We've never done this calculation. So of course, you're going to have to actually calculate that in your code before you run your loop. You're not going to want to do it every single time. So you're not going to do it in here. You're going to do it out here. And so that calculation will be like M equals to, and then I think there's like numpy.floor or whatever in Python is just N over B. So that's how that would work. Okay. Thank you. Okay, so yeah, this turns out to be kind of a good idea to do something in between. And we can also just do like the computation analysis as well. So if we look at like computation for mini batch gradient descent, it's unsurprisingly very similar to the gradient descent case, where it's going to be big O of, and now, if you recall over here for the gradient descent case, we had like number of epochs times data set size, because inside you had this sum, right? Inside you had, for each one of these, that was where the t came from, you had this sum, which was where the n came from. Well, now you're going to have an internal loop for mini batch gradient descent that does this m times and breaks it up into size b things. But at the end, this m times b is basically n. So you end up with t, instead of n, m times, capital M times b, and what's the last guy? The dimension d. And in batch gradient descent, we had t n d. And this is just equal to n, right? Basically. And so what I was alluding to is that, like, yeah, I'll just write in words, is that in practice, what happens is that in practice for the same, so if you fix your number of epochs, so like for the same t, mini batch gradient descent for the same number of steps usually finds a better W. And this is, of course, for the case where you've chosen B to be something less than N, and you're gonna like you kind of sweep over a bunch of different values to find what is the best choice. And by better, obviously this means that the actual empirical risk goes down. So it's like if you graph this plot over here, for optimization, right? We're trying to minimize the empirical risk. It means if you plot this with the same number of steps t, the mini batch gradient descent plot would go down faster. Okay, maybe I draw that plot. It seems like a useful thing to add. So we saw the batch gradient descent version. So now I should, yeah, I'm just going to label like this. So this was like the batch gradient descent learner. Then let's say you chose like a good mini batch size, and your plot maybe looks like this. So now for like the same t, maybe you chose t to be, maybe this is the t you chose for some reason. And then for that same t, you can see that the empirical risk is indeed smaller. And then, so this would be like, let's say, mini batch gradient descent with, I don't know, maybe b equal to 32. This is like not uncommon choice for medium-sized applications. And then if you do the other extreme, which is like stochastic gradient descent, then you'll find that it'll probably do worse than the batch size of 32. So maybe something like, I don't know. It doesn't have to do worse than the batch gradient descent case, but this is just an example of something you might see. And so this would be like stochastic gradient descent. So there's kind of like a sweet spot usually. And that's what it's saying. Okay, so with all that being said, those are kind of going to be the algorithms for the course. And in some way, they cover a very large part of what is really used in standard supervised learning applications without a lot of the bells and whistles that I've already talked about. Like you use different initializations, more complicated step sizes, things like this. Okay. So the next thing now to add and discuss is the choice of function class. And In particular, should we always be picking linear functions? And the answer is obviously going to be probably not. So let's imagine we want to predict I don't know. This is the example I came up with. So we have the age of a car. Okay. And the label is the price. It's still doing regression. We're going to do all this stuff for regression, and then in like 4 classes or so, we're going to finally get to classification. See, you just changed the loss. Okay, so what's going on here? Well, this is my random guess at how the price of a car works. But you buy the car, and at the beginning, it's expensive. And then it quickly degrades in price. And then it just keeps going, and it's not like that bad. But at some point, it gets so old that it now is called an antique. And then it slightly increases maybe in price because it gets this antique status. Okay, so maybe it looks something like that. So first of all, maybe this thing is like not even linear. Maybe it's kind of like this kind of curve, and then it slowly has like an increase. Okay. Point is, so far we've been restricted to lines. And maybe your best choice for a line is actually going to be something like this, which is kind of disappointing, right? And so what you really want is maybe a function that looks kind of like this. Wow, it actually made the curve this time. So that's the motivation. And what does that mean? We're going to want to change our function class to include more complicated functions. And kind of the natural way to do this, to continue with all the tools we've learned and all this stuff, like because we calculate all these gradients and partial derivatives and so on of linear functions, turns out we can reuse all those results if we move to like what is called this polynomial regression setting. So we still want to do like regression, but now we're going to use polynomials. And hopefully now at the beginning of this course, when you had to learn about how to write sets of functions that are a polynomial of degree 3 or less, or things like this, you'll see why it's useful. And the idea is maybe here a quadratic function is a good idea. And then maybe other cases like you want something like this. And you might remember from Taylor's series that eventually if you pick high enough order polynomials, you can really approximate kind of anything. Okay, so that's the story. We're going to want f to contain more complicated functions like polynomials. And let's see how this works in the one-dimensional case with an example, and then we will generalize. Okay, so let's start with dimension 1, which is what we saw in the example above, right? Remember, our features are going to be in Rd plus 1. That's R2, because we have this index 0 value that's always 1. And then the labels are just R, as they are in regression for us. Okay, so the thing we've been studying so far, and like in the above case, we had this linear function. So far I'm just writing what the linear function looks like to kind of compare visually, or I guess symbolically, what the like equation, how it differs. So you got this linear function, and in this case, that will look something like for some new feature x, you take its dot product with a parameter w, and that'll equal to, the feature, remember it's 1 in the 0th index, then it's x, what did I call it, x1. Then you take its dot product, which I guess that's the row vector. Take its dot product with the column vector of w0, w1, right? Which is just w0 plus x1, w1, which is your equation of a line. This is your y-intercept, this is your slope. We've seen this a bunch. Okay, how is this going to look for the polynomial case? Okay, and before I get there, apparently I really want to make this verbose, which probably will help. Okay, so far we've been calling this f, because we're changing the function class. So I should probably write how the function classes look. But in this function class was the set of all functions that contained functions of this form, right? So it was like all the functions such that functions map from R d plus 1, which was 2, unto R, such that f of some feature x was this x transpose w, this dot product, where W, this is going to be important for comparing, W was in R2 because it had to multiply, we needed this y-intercept and it needed to multiply the one feature. Now their function class. So now let's compare this to a degree 2 polynomial. And that was like what we saw in the plot above, this purple thing. So maybe that thing above was really a quadratic function. So that's a degree 2 polynomial. All right. How is that going to change? Well, you're going to have an equation that looks something like W0, just like before, plus x1. And maybe let me write it in this way such that it looks, this is W1 multiplied by x1. So W1 is like the slope that we've seen before. And then all I'm going to do is add on a quadratic term. I'm going to square the x1. I'm going to have x1 squared, but I'm going to need a new kind of parameter for that. So there's going to be W2 now. Okay. And this indeed, by changing W0, W1, W2, you can describe any quadratic, any parabola function. So we've kind of enriched or improved the expressive power of our function class. And so what's our function class going to look like? Well, our function class is now going to be different. It's now going to be from R3. No, sorry. Still from R2, everything's fine. We still want functions that take in the same dimensional features, obviously. But what's going to differ now is that this is not X transpose W anymore, right? And what I wanted to write is that above here, you can actually look at this thing in the same kind of view as what we saw here, except now adding a third dimension, right? Which is now I can look at this as 1, x1, and now I add a third kind of index to this vector, which is x1 squared. And then I just take the dot product with W0, W1, W2. Right? Hopefully you're convinced that these are equal. All I've done is added a third term, and now that's just bigger vectors. The beauty of this is that this just looks like a linear function where your original features were the following. Okay. And so now your original function, f of x, okay, I'm going to introduce one more notation to make this, because we're going to keep using it forever, which is, you can think of this thing is like a function that takes in x, this kind of thing, and produces a new feature, like a bigger feature. And kind of the bigger the polynomial, the more terms you're going to have. And often that's denoted with this phi, this Greek symbol phi, kind of for feature. This is really commonly used for, and it's called like a feature map. And what it does is it's going to take in the original kind of x vector, right? And it's going to produce the thing above. Oh, so that's going to be the phi. Cool. So you take its transpose, because now the default is it's a column vector. So you take its transpose to look like a row vector like this. And you multiply it with the corresponding W vector, which I'll write still like this. Yeah. Hopefully you're not confused why it's double transposed, because when you write it out, we consume row vector. So when you transpose, it's now column vector. When you don't write it out, you assume it's column vector. So you transpose to make it a row vector. Okay, just now some notational. Okay, let's just finish one thing. Function class. Now your function f. The reason I've introduced all these is now everything's going to be like before. But now this is not going to be x transpose, right? It's going to be phi of x transpose. So you're just mapping your feature into a higher dimensional feature. You just kind of introduced this like squaring and so on. You can introduce the cubed version and things like this. And now your parameter vector grows. It becomes in R3. Okay. Now some notational remarks, because you can imagine you want to keep pushing this to degree 3 and 4 and 5. And you want to kind of have like a way to, distinguish between which function class is using what. So we add subscript. So we're now going to call this phi2, because it maps, it just squares things. If you do phi3, it's going to be the cubed version and so on. And the function class is now going to be subscripted with 2 for second degree polynomials. And you can imagine it's going to change to 3 and 4 for higher order ones, and this is phi2. And we're going to call the linear one sometime, we're going to now from now on call it f1, which is you'd use degree 1 polynomials. And we're going to really, so you're going to have to remember what these subscripts mean. It's going to mean the degree of the polynomial you use, because we're going to study how growing the function class is going to affect all sorts of things in the following lectures. And another way to think of like just this x transpose is the same obviously as phi1 of x. Phi1 just maps it to the same thing, right? By the notational convention. And so now I'm just going to just do this one more time for degree 3, just so you can really see what it looks like. And once again, thank God we're using the iPad, so I can just copy and paste and show you what changes. So I'm just going to change the color, I guess. Actually, let me make it to something different that we can draw above. Okay, so that's going to change to degree 3. And the thing that's going to happen is now we're going to have a W3 x1 cubed. This is obviously going to be bigger. And yeah, so we get an extra parameter. Now it's phi3. The definition of phi3 is this. We'll get to the general definition for any dimension, any choice of polynomial degree in a moment. And your function class is now f3. Still functions, right? From like still taking normal features, two-dimensional features to things, to labels. But internally, it's doing this mapping to a kind of more expressive set of features. It's adding the cubed feature now, and your W is now in R4. Okay, so yeah, this is how we're going to be kind of gaining more powerful functions. Yeah. Right, so we're going to talk about the empirical risk of the different functions in a second, of like doing ERM, right? ERM uses a function class, and we're going to talk about how does ERM do if we change the function class, which is what we're going to do. But visually, you can see what's happening, right? Because you should remember that this term, this L hat of some function, is representing how well you fit the data, right? It's the empirical risk. It's like literally the measurement of the squared distance of all this. So you would expect that you can write this, from this picture, what you would expect is that the purple F, right, those are the purple F, should have a much smaller empirical risk, like, so how it's written to be, well, just, yeah, smaller than the empirical risk of the red guy. And so this is the motivation to use a bigger function class, because if you do your ERM with it, you can find this thing. You can find this F. This is hopefully the F ERM will output. But if you restrict ERM to only search over linear functions, as we've been doing before, I don't care how long you run gradient descent, or if you do your closed form solution, the best thing you're going to do is output this line, which is not going to fit the data very well. Okay, and just keep in mind, all we're trying to do so far in these lectures, at least like this optima, is we're just trying to fit the data set. Okay, we're going to talk about this at the very end about doing well on new data. But for now, I really just want to fit this data, like the data, as well as I can. Okay, because I told you that the empirical risk is a good estimate of the true risk. So I just need to optimize the empirical risk, and I'm done. At least that's the idea for now. Okay, so that's why we want to grow this function class, and we're gonna see that like so far our intuition is telling us, why don't we just grow it indefinitely? But before doing that, I just want to like, you're gonna need to know how this phi function works and what the dimension of the parameters are when you have more than d equal to 1, if d equals 2 or 3. So I just give you one more example, give you the general formula, and then we come back to this story that we've been trying to build up. Okay, so one more example, because I think through the example it's probably easiest to see, instead of just giving you this equation for what the dimension is going to be of the parameters, which I will do. Okay, so let's do d equal 2, and this should be enough to give you the idea. So as before, this x is r of d plus 1, which equals to r3. and y is still r. Okay. Let's save some time by copying things. So linear functions, everything's the same as we've seen before, basically, right? The only difference is you get, okay, I'm just not going to write this. I will write this. You get an extra guy, x2, right? Because now this thing's in R3. So this is what we've been doing. Nothing new so far. This is exactly how we would have dealt with it in the linear case. And you end up with W2 x2. So you have two-dimensional features with a bias term. And yeah, only thing that changes in our function class is now the features are from R3 and the parameters are R3. And these things match because they're dot product, just like before. Okay, now the more interesting thing comes when we do degree 2 polynomials. Because for degree 2, it turns out you're actually going to kind of want to consider all sorts of, all the possible pairs of things. And we'll see what I mean by that. So let's do that. Okay, degree 2. So far we saw this, but now we have an x2, right? So let's introduce it. And I'm going to need some more room, so I'm just going to move all of this down. Okay. So we had this in the linear case. And then in the one-dimensional case, we just added this, right? And we're still going to add that. It's going to be W3 now. We're also going to add the case for W2. Okay. But we're going to have to add one more term, which is in the dimensional, like the multivariate case, polynomials of degree 2 means also including the following term, which is x1 times x2. And this is a degree 2 term because you will, for all the variables, these are the variables that it's a function of, you should add up all the exponents. And these are both 1s. So if you add them up, you get a degree 2. You can already see that when it gets to degree 3, this gets a lot messier because you would have had x1, x2, x3, x1 squared x2, x2 squared x1, x3 squared x1, all these different combinations, and it just gets quite out of hand. And the purpose for doing this, like intuitively, is that you want to model relationships where growing one of these can simultaneously like kind of affect the other one as well. Okay, and the way somehow I had a good example, a better example than the one I'm going to tell you before the class, but now I forgot it. So I'm going to tell you the one I said last year, which I didn't love that much. But like, here's the story. It's like maybe a relationship is like you wanna grow your crops and you're a farmer, and you've got you spray fertilizer. That's like one of the features. How much fertilizer do you spray? And the other thing is like how much rain do you get? And for some, I don't even know if this is true, but in my mind, this was true, which is that if you sprayed fertilizer, then there's like this kind of relationship that the more fertilizer you sprayed, or let's just say it this way, for every like, let's say, I don't know, gram of fertilizer you spray, if it rains some amount, then you make like, then the crops will grow some amount. If it rains more, then it's going to grow more. But if you like sprayed more fertilizer, then the effect of the rain actually scales like even more. So like, the rain affects the fertilizer in this multiplicative way. Yeah, so it's not like basically, if you had, let's say, sprayed 1 gram of fertilizer, then the effect of the rain for that case should be much less than if you had sprayed much more, because the rain like kind of amplifies that the amount of fertilizer you had there. Okay, and that probably was not a great example. So I'll hopefully remember to next time come up with an even better example. And that'll hopefully motivate this more. I'm getting some likely spam call. Okay. So But the point is, you're going to want to, like, hopefully you get the intuition that you're going to want to consider kind of all these different relationships that these features will have. Where if one is growing, then maybe the other one also, like, its growth is affected by how much the other one grew before. Okay, and now this calculation becomes a lot hairier. So let me just write it all out. Oh, actually, yeah, I'll write it out. So you create a new feature that now looks like x1, x2, x1 squared, x2 squared, x1, x2, right? These are your new kind of features that you have. And the weights or the parameters you have, well, now you have 5 of them, I think, yeah. Well, you have technically 6, because it's indexed up to 5. W3, W4, W5. Okay. And now this phi2, same function, but when it takes in x vector of this form, right, which is a vector in R3, it does the following operation to it, right, which is it produces all of the degree 2 polynomial features that you can create. Okay. So this phi2 function, depending on the dimension of the input it takes, will do this kind of different operation. And that multiplies the whole same thing. And the way the function class looks is exactly the same as before. Okay, so this is hopefully pleasant, except now input features are in R3 and W is in R6. And so you should already see that this is not matching the input features because this phi2 function now maps it to a higher dimensional feature space. And this number is clearly going to be a function of, you know, what is the choice of D and what is the choice of polynomial, which in this case is 2. Okay, and so hopefully that makes some sense. And also, the thing you should have observed earlier, where is it? Hopefully, and this is a general, yeah, I guess I can put it here. The general trend that what you'll see is that F1, which is all lines, this function class, is smaller or equal to, well, actually it's just, yeah, it's strictly smaller than the class F2, which has all polynomials of degree 2 or less, right? And in particular, you can see it as follows, right? Let's just go to this 1D case. If you look at these functions, you had here things of this form, which are just like a line. Here you had this extra squared term. If you set W2 to 0, you just get back any setting of the line. So this class is strictly bigger. And this is important. So now you get new functions. They're all the polynomials of exactly degree 2 are the new functions. And then this relationship keeps holding indefinitely. You keep getting new functions. Okay. And now I tell you the general kind of form of this phi p function, right, which is all you really need, which is kind of like what is the degree of it. And the calculation for it is you just consider all possible combinations of things. And in the course notes, I have like an actual pseudocode algorithm to do this with a bunch of loops. There's more efficient ways to do this in code, but it's much less like intuitive what's going on. And in your assignment, you're gonna have to kind of like code this phi function. So there you should refer to those course notes to do this. Or just Google it, like it's kind of a very standard thing. Okay, so yeah, in general, the way this works is that this phi p function, p is for the polynomial degree you're gonna use, is gonna be a map from the original feature space x to some new space z. Okay. And yeah, this is a degree p polynomial map. And here p is just like some natural number. Okay. And the way it works is like this. So if x is equal to r of d plus 1, which is all we're going to deal with, then z is going to equal to something clearly larger than d plus 1, or at least equal to if p was 1. And that is, I'm going to call this r of p bar, which is kind of like the number of new terms based on that p. And then all I have to do is tell you what p bar is. And the calculation for p bar will be based on d and p, as we have seen. And it's sort of ugly, and I'm not going to get into the details of why it's like this, but it's going to be d plus p, choose p. Okay, so this is like a combinatorics thing. You can plug this into a calculator. Yeah, for the sake of time, I don't think I'm going to get into it, but it's just counting all the possible combinations, right? Of if you want to consider degree p things and you have d features, it just counts all the possible combinations of if you just have a degree 1 polynomial, and then how many exactly degree 2 polynomials can you have by multiplying every pair, and then how many degree 3, which is all possible 3 multiples of things, and so on. And this turns out to be the calculation. Okay. And just to, drive the point home that this is indeed correct, in the cases we had above, let's just double check that things checked out. So for d equal to 2 and p equal to 2, which we saw above, right? Well, that implies that what is p bar going to be? Well, p bar is going to be 2 plus 2, choose 2. And that is 4 times 3 divided by 2 factorial, which is just 2. And that's 12 over 2, which is 6. And hopefully that matches the 6 here, because we had 6 terms here. And that's like the more general formula. And this calculation will be useful because when implementing all these possible combinations and stuff, you're going to want to do this calculate this first and then implement a variety of for loops to kind of do all these cases. And yeah, in general, your function class will just be the p version of this. So in general, you have fp. It'll be a map from r d plus 1. And this will use phi p. And this will be p bar. So p means you're using the pth degree polynomial map, which gives you all the features up to degree p or less. And that gives you a lot of features, and this p bar tells you the dimension of your new parameter. Okay, and so yeah, we saw this relationship above, like this. And okay, so we had all this, we came up with all these new function classes, but we need to run ERM with these new function classes, and what does that look like? And it turns out that because of this interpretation that this just gives you a new feature that's higher dimensional, and this just now looks like a dot product, it turns out that everything we did before is going to work exactly the same. And yeah, so let's see how that looks. So we're going to have a learner. So this is kind of the end of explaining these function classes. Now this is the actual ERM learner. So we have an ERM learner, it takes in a data set, right? And the ERM learner is based on a certain function class, right? That was required because that's what you're going to do the minimization over in the optimization step. And so to kind of specify the function class, we're going to put, I guess for just for here, we're going to specify it with subscript p. It means I'm going to run ERM, my learner, with function class of degree polynomials up to p. And so the way this is going to work is now I'm going to output an f hat of p. And what's this f hat going to be? F hat p going to be? Well, it's going to equal to the arg min f as before from our function class f. But now we replace f with fp, right? Because that's what's changing here. And everything's the same. It's still L hat of f of p. And what is the story here? Well, it's kind of the same story as before. So what you can find is that, since the function class is of a certain type, and you know what the types of functions inside are, and you notice that every single function in the function class has a form that is determined fully by the single parameter vector that it's multiplied by, right? There's this one-to-one correspondence with, if you give me any function in this class, it must be of this form, which means it must, if I just know this parameter vector, I know the function immediately. Of course, you have to tell me that, like, what degree are you using, because then I'll use phi of p. But other than that, all I need to know is this parameter. And in the other way, if you give me a parameter vector, I can always construct a function of this form, and the set, basically the set of all parameter vectors will give me back this function class, and vice versa. Okay, so hopefully you're seeing this again, this very important thing that searching over function classes, if you parameterize them like this, it's just searching over the parameters. And so the equivalence is the following, which is this is the same as minimizing over W vectors now in R of P bar. And of what quantity? Well, it's going to be the empirical risk with the corresponding function type plugged in. So we have 1 over n, sum I equal 1 to n, of what? Well, let's just do a general loss function. And then our predictor is of this form, phi of p, right? This is the only thing that's changed from before. Now we have this phi of p, which just gives us a potentially larger dimensional vector if p is larger than 1, multiplied by w, compared to xi, yi, like this. So exactly the same empirical risk as before. The only thing that changed, instead of just having xi, we now have phi of p applied to xi, which gives us a higher dimensional feature if p is greater than 1. And if p is equal to 1, everything is the same, right? And so how does this work? Well, now, this is an observation. So to get this argmin, it will turn out to be sufficient, or this, like this above observation kind of implies that f hat of p is simply equal to, for a particular feature, phi of p. So you're going to, like, if you have a new feature, what you're going to do is you're going to pass it through your feature map, right? Because you need to map it to this new dimensional features. That's how you're going to use it. Then you're going to multiply it with the corresponding W vector hat that you get from solving the above argmin version of this problem. So this is just like the learner we had before, where now you're going to want W hat to be the minimizer of this, right? So u equals to this, where W hat vector is equal to the argmin, the W that minimizes this quantity. And this is just like before. And guess how we did this before? We could either get the closed form solution if our loss was of the form we wanted, like the squared loss. And it turns out that because we just mapped to a higher dimension, you can get closed form solutions. But now D becomes P bar everywhere, right? So now you got way more dimensions. You can imagine calculating all those inverses and everything. Way more expensive because you replace D with P bar everywhere. And you can also run gradient descent in the same way. But all those computational costs are one thing that is already growing, right? Because D goes to P bar. And so you can, so then you can solve for W vector hat using closed form solution or gradient descent. Well, actually, I'll write them all. Like you can do batch gradient descent, mini batch gradient descent, stochastic gradient descent, choose whatever you want. So hopefully you're seeing this kind of like compartmentalization of the different kind of things we can do and how we can vary each of them. And then you can imagine there's all sorts of things that play better with other things. And like if your dimension was small, then probably you're fine with the closed form solution. It's not that big of a deal. The dimension starts growing a lot. You're like, oh dear, I really do care about this computation. Maybe the closed form solution isn't the best because it had this D cubed thing, if you remember in the big O. So maybe you don't want to run that. You choose one of these. Okay, so that's one thing. So first of all, like, here's our first kind of trade-off, which is like, as P increases, computation increases. So that's maybe like the first kind of downside to increasing your function class. But let's just kind of forget about computation for a moment and see how this works through an example. Just forget about computation. Imagine we like just solve the closed form solution. We had infinite compute and talk about what happens then. And do this through another plot. And this will hopefully show you why we also, well, it's been said many times, but why this increasing these function classes helps. So you have a data point, let's say here. Okay, it really doesn't matter where I put them. Say you had like some 5 data points like this or something. I don't know. So you start with your first function class, your lines. And yeah, you've tried to fit a line, and the line's like this. And that's going to be the, let's say these are all the closed form solutions. So this is like, this will be F1, let's say. Yeah, this is F1. This is, let's say this is your closed form solution. So it's like the best possible fit to the data points. And that guy will have an empirical risk, L hat 1, or actually forget, there's no 1. L hat of F1, which is this guy. That has some empirical risk. Okay, so now we pick a bigger function class, right? And suppose we solve for the closed form solution. The first observation you should have was that, and let me just write it here. Well, I'm going to write it below. Is remember this, F1 is a subset, strict subset actually, of F2, and so on as we keep going. So what that means is that if I perfectly optimize, right, I get this closed form solution, then F hat of 2, which is the minimizer from this set, which is a bigger set, can be no worse than this one, because at the very least I could have chose the same line. So there's no way that the empirical risk of F hat 2, if I perfectly optimize, can be any worse than F hat 1. Because once again, the argument, like empirical risk minimizes over a function class, and this function class definitely contains the minimizer of the previous function class. So this is a big observation, first of all, that this empirical risk will be at least as large for F1 as it's going to be for F2. This will be F2. Let's draw F2. So F2 is going to be this quadratic function. And yeah, it could be a line if a quadratic doesn't really help. And maybe in this case, something like this is somehow better. I don't know. That's supposed to be a quadratic. There's not supposed to be any of these bumps in there. Okay, that's F2. And you can, keep taking this onwards until you get to like a really high P. Let's say we chose P to be like 10 or something. I don't know. And what is that going to look like? Well, you can imagine, eventually, you can get a function that fits your data points perfectly, right? And it might look like that. So this should have, like, literally fits it perfectly. Eventually, if you pick P large enough, you're going to get to this guy. It's for very large P. And that'll be approximately equal to 0. And if you make it really large enough, you can fit it perfectly, and you will have 0 loss. So this is going to be F hat of P, F hat of P, for very large P. Okay, so forgetting about the whole like computational business, if we want to minimize the empirical risk, everything should tell us that like, well, P, we should just make P very, very large, because we can get to 0 error. And then that means that, that's great, because now we can, well, if we believe that this quantity is indeed a good estimate of the true risk, that means on new data, I'll also have 0 error, right? But of course, like, that's probably not what you expect. Like, maybe the true trend of data is something like this. Okay, maybe I draw them bigger, something like this, let's say. And then you're like, huh, how did that happen? My red function really does not do very good. on new data points. And I mean, of course, for the new data, it's like this true expected risk. So you'd have to draw like all the infinitely many possible samples to get like an idea of it. But and this purple one seems to be doing better, but it had an empirical risk that was higher. Okay, so that's kind of an observation. And yeah, I guess that's kind of where I leave you with this cliffhanger. So the next class, we're going to talk about how this happens. Clearly, you can see that if you make the function class richer, you run into this problem, which I'm going to give it the name it is used for it, which is called overfitting. You kind of like overfit to the data. And clearly, this guy cannot be a good estimate of that true risk anymore, right? Because if it was, then the true risk would also be 0, and there's no way that this guy's true risk is 0. It's like so far away, right? So that's that. So we're going to somehow see that you're going to need to balance, even forgetting about computation, even just based on if you had infinite compute, you're going to somehow have to balance how complicated your function class is so you don't overfit to the data with how, yeah. And also you're going to want to complicate it enough such that like a line is probably not a good enough choice here, right? And this will be called like underfitting. It doesn't fit it well enough. Okay, yeah, let's end there. Next class we'll pick up with this whole thing, and the next section is called like model selection or function class kind of selection.